will talk about something that we are describing as Sparsistent filtering of co-movement networks, from high-dimensional data. There is a joint work with Chakrabarti, who is a postdoc, working with me. Our names look very similar, but we are not related in any fashion. What is the problem that we are interested in, and what is it that we would like to analyze here? So let me just give you a few very basic definitions just to set up the stage. And for the whole audience, I guess it's not very important to describe networks in great details. Everyone knows about it. But in particular, what we will be dealing with in this presentation is something called co-movement networks, which is basically which we will there is a large literature in sort of statistical finance which deals with this kind of networks. So I would like to just maybe visually describe what kind of networks I'm talking about, and then I'll get into the problem. So this is what you are seeing here on the screen. This is the S&P 500 index from 2002 to 2017. So it's 16 years worth of data, and these are daily closing prices of the index. So whatever is reported as the S&P closing price for a given day. So the market opens in the morning, then it closes maybe around 5 p.m. or something like that. So whatever the price that is quoted at the very end, that is taken as the closing price, and we see that it fluctuates a lot, etc., etc. So what we are plotting on the y-axis is literally that S&P index. So for those of you who are not from finance, S&P 500 is basically a combination of 500 different assets which are all registered in the New York Stock Exchange, and it's a weighted average of all of their different prices. Generally speaking, it can be thought of to represent as a, it can be used as a kind of a barometer of what the traders are doing in the market. So what we see is that, just to give you a sense of the x-axis, every year, roughly speaking, there are 250 trading days because the weekends are closed, and then there will be some other days where the trading will be off. So 250 into 16, you get 4,000. So roughly that is the dimension on the x-axis. So what we see is that, one obvious thing is there, which is the 2007 to 9 financial crash. But generally speaking, what people have thought about is that these kind of processes clearly show something called it has a random walk component, or from a financial econometrics point of view, this can be described as having a unit root, so which has this explosive tendency. So these are non-stationary processes. So one of the very easy ways to convert it into a stationary process is simply to take the first difference, which can be described like this. That you take the log difference, and then that becomes the return series. That is also called the log return series. The moment we convert it into return, then the same data which was plotted here, this data set, this basically looks like this. So on an average, the return becomes close to 0, and then there is a bunch of fluctuations around it. Now, one of the key observations, and this is very well known in the financial data, is something called volatility clustering, that when the market gets volatile, it tends to remain volatile for some time. And when the market gets becomes relatively more calm, then it tends to remain calm for quite some time. So as we can see that during the dot-com bubble, the market got very volatile. And the 2007 to 9 financial crisis is an obvious example where, again, it caught into a long spell of volatility. So what the financial networks, what it started looking at is that there are, just to clarify, there are two types of financial networks one can think about. One is that literally, firm to firm, or financial entity to financial entity connection through, let's say, asset cross-holding or other types of connectivities, which can be where the linkage can be real in some sense. These are not statistically inferred. But what I would be looking at is more like the inferred connectivity. So what do I mean by that? The idea is as follows, that if there are n assets, so for example, in the earlier case, if you take S&P 500, then this n was more like 500 assets. Now, this is what represents the average behavior. But technically speaking, what one can do is that, one can look at all of these 500 different assets separately, and each of them will give rise to a time series. So we'll have 500 time series of, let's say, some given length. Now, once we do that, then from that, a pretty standard, idea is there, which is that, let's say I denote the, return data, which may look something like this. I'm abusing notation a little bit. So what I mean is that N is, let's say, also a set of, all the stocks that are there, all the assets. And T, capital T is the, number of time points for which we have the data. Now, from this, one can construct something like a, covariance matrix, or let's write it by S, or let's say a correlation matrix. Now, there is a lot of literature on analyzing this disaggregated kind of network where all the nodes, now I can, I guess, go back to the first slide, where these kind of financial networks are there, where the stocks are the nodes, and some functions of correlations represents the edge weights. So, and one very intuitive way to think about it is that suppose there is absolutely no correlation whatsoever, in terms of returns between two stocks, then there will be no edge or link. So if you do that, then this is a very simple, example that if you have 50 stocks, if you are plotting the network as a whole, then this is what you get. Now, one can, there is a little more nuance to it, because if someone just takes the correlation value and says that suppose this is the edge weight, then there is a problem, because correlation values can be negative as well. So can we treat it as a metric? The answer is no. So you have to take some kind of transformation of the correlation value in order to come up with a reasonable description of the network. But the key point that I'd like to sort of summarize here is that that can be done very easily with some very simple metrics, and the whole network the market as a whole can be described as a network. So this is a network inferred from what can be described as the sample covariance matrix. Now, this is the object that we are interested in. Now, what is the question that we are interested in? The point is as follows, that if you look at this whole thing, it's not very, meaningful, in the sense that there can be, two types of problems, or rather actually three types of problems. Let me give you the first problem, which is actually the entry point of our algorithm to begin with. The first point is that there has been actually a lot of debate about this, that if the markets are, evolving in such a volatile manner over, time, then is it even fair to take time series which covers volatile and non-volatile period? So in the sense that, in order to find out the correlation value between, let's say, a pair of stocks, you need a reasonable length of time series data. So let's say you take 4 years window, which is a very standard, window in this literature. Now, suppose that 4 years starts from 2006 and ends in 2009, or even more extreme case, it starts in 2008, ends in 2011. The problem is it's sort of contaminated. There is some contribution coming from, very volatile period, some contribution coming from not so volatile period, and potentially one can actually argue that it's not as if, like, if you just control volatility, then things will be over, because then there is a big the point that one can make is that maybe the market structure itself shifts by then. So 4 years is not a short time. Now, then one can ask, why 4 years? Why not take 1 year? Then the problem is that suppose you have 500 assets, you have only 100, time observations, 100 days worth of observation. Then the sample covariance matrix that one can estimate will be a very bad estimator of the true covariance matrix. This is the basic problem of high-dimensional statistics, that if the number of observations, number of entities that one is observing is very high, but the number of data points that is being observed is very low, then there is a problem. You cannot estimate the covariance matrix in a credible way. So I will show you what is the problem with that. I will give you a very specific example. Now, this is the first problem that we want to address. That suppose you really chop it down to a very small data set in terms of time length. Then what is the most credible way to infer a network from the covariance matrix? The second problem is that, is there a way to, if you just look at this picture, it's just a blob. There is a bunch of points and which are connected to each other. Is there a way to get rid of much of these, many of these linkages which are potentially non-informative? And not only that, we can actually ask, two questions here. The first one is that suppose these are just some correlations that are statistical in nature. So this is more like the motivation comes more from a point of view of filtering. That suppose there are just some spurious connections. How do we get rid of them? That is something that the literature has talked a lot about. So in that way, we are not the, let alone being the first one here, we are actually late entrant here. But the bigger question that one can now ask is that what if we could remove even some true edges, but it's just that they are not particularly strong enough. Maybe they are there, but if we remove them, is it possible to infer a more clearer picture of the true underlying and strong connections that describe the network? So I'll give you a visual as to what does it look like. So what we are saying is that at the end of the talk, maybe in another 15 minutes, what I would like to convince you is that if you start from here, which is the given network, which looks very messy and entangled and so on, we want to propose an algorithm that will give you something like this, where it's basically the exact same set of stocks which are there, and all of these connections are subsets of what you find here. There is no new connection that is being added. It's just that all the sort of what we will describe as unnecessary connections. Now, what is unnecessary is something that we will define later. But whatever we describe as unnecessary connections, that will be taken out, and only some of the key connections will remain. So we will. The purpose of this paper is just to propose this thing called Sparsistent filtering, which will allow us to do that. The good point about this whole thing is that this is. Let me also say it clearly to differentiate it from the existing algorithms. There is a lot of algorithm which allows you to do filtering on this kind of networks, or even covariance networks that can be there. The difference here, and that is, I guess, our probably the key contribution, which is that they do not have good small sample property. Here we have that, so this is actually useful that way. Okay, so here is something that I do not want to spend a lot of time on. So there is a the spectral structure has been studied a lot, and especially what people do is that they use this Marchenko-Bostov theorem from random matrix theory to filter correlation matrices and so on. Given that I don't have a lot of time, I will just move ahead and get to our basic point. The eventual goal of, technically speaking, what we would like to generate is that the adjacency matrix of the network has to be sparse, and the spectrum of the adjacency matrix has to be close to the true covariance matrix. Now, there is a problem. The problem is as follows, that if I am simply observing financial data, how do I know what is the true data generating process? So if it is purely, we cannot really, we do not know the philosophically whatever is the true data generating process there, right? So we have to have an analog for that. So the way we proceed about it is that, so here is the basic problem and that you'll find for high dimensional data, that here there is a little bit of notational problem. So think of it this, let's ignore this notation P and N. Let's just consider N stocks maybe, and T time points. So the idea is that if this T is substantially greater than N, then whatever covariance matrix that you can estimate, that will have all the good properties. But if it so happens that this N is actually much smaller than T, sorry, it's the other way around. N is substantially greater than T, then this covariance matrix that you will estimate simply from that you can just calculate from the sample, that will be biased, and that will have a lot of problems in terms of its convergence to the true covariance matrix. So here is a simulated example that if this T is almost 10 times of N, in that case, let's say the true eigenvalues that you can decompose, and that should be 1. Then if you just rank order all the eigenvalues, then you know that they are by and large around 1. There are some fluctuations. Ideally speaking, they should just be a horizontal line like this, but they're still somewhat close. But the moment it goes to 0.5 or this kind of things, So here n and t are exactly equal. If you construct the covariance matrix, then the eigenvalues are completely off. From what should be just a horizontal line, it's just completely off. So this is the main statistical problem. Now, how do we deal with it? This has been recognized in the literature, and the key to that is that something that is known as Stein's approach. What it does is that it takes the covariance matrix and decomposes it, finds out all of these eigenvalues, and by hand it compresses it towards one. So this is a very mechanical idea that that it will be biased. So what you do is that construct the covariance matrix, do the eigen decomposition, find out the eigenvalues, and then by hand push them closer to one. But then it has a lot of problems. So then there was a very famous idea that came up, something called Ledard-Wolff estimator. It has all sorts of good problems and a set of very good optimality properties as well. I'll not get into that. Roughly speaking, the idea is that it takes the sample covariance matrix and some other positive definite matrix. What they showed is that positive definite matrix can simply be the identity matrix, and you can choose this weighted average of some optimally chosen alpha that gives you the closest to the known data generating process. So it has all sorts of good statistical properties for this high dimensional problem. The third thing that was proposed is something called thresholding. Again, I will not spend a lot of time on it. Intuitively speaking, what it does is that it takes the covariance matrix and then puts a threshold. If some values are above that threshold, keep it. If those values are less than threshold, make it equal to 0. Now, this thresholding is actually very intuitive, and it's very common in the networks literature because this is the easiest way to filter, right? Because if you say that, suppose I go back to this picture and I say that, well, so if the covariance between some I and j is less than some threshold, let's call it tau, I will make it equal to 0. Then immediately that gives you a filter. But then that is a very ad hoc estimate, right? So what we are doing here, as this is our algorithm, that we are being a bit greedy. What we want to do is to retain the property of this threshold estimator because it's very easy, very intuitive, but it has its drawbacks in terms of being very ad hoc. So we do not want that ad hocism. So what do we do? What we say is that our proposed estimator is basically that from a given sample covariance matrix, you first find out whatever is the Ledard-Wolff analog, because that is something that we can very easily calculate, and it's all of its good properties are there. And then at every point of time, let us try to get close to it by thresholding it one after another. I mean, edges one after another. So mathematically, what we mean is that this is the optimization problem that we describe. Let me just directly get here. That what we want to do is to reduce. This will be the argmin of the spectral distance between the true covariance matrix. Between the sample covariance matrix and the Ledard-Wolff analog. We want to reduce the distance between them because we know that the Ledard-Wolff is the potentially it has all the good properties. So that is something that we would like to target. So we would like to minimize the distance between them. How do we minimize it? We just peel the network one after another. I mean, peel the edges of the network one after another. Based on, first we remove the weakest link, then see whether the spectra gets closer to, so it's like, reduce the, edge, let's say some ith edge, which is the minimum width. Find out whatever is the spectra and find out the difference between the Ledard-Wolff and the thresholded matrices spectra. If you are getting closer, then remove it once more and keep on doing that. But then the more I am peeling of edges, technically speaking, we can give a cost because this is also loss of information. So for that, we are attaching a cost parameter associated with it. Let me just visually diagrammatically explain what is going on. The idea is that this blue curve, let's say, represents the cost of edge deletion. Now this is parametric. If you don't want, let's say that the cost of edge deletion is 0, you can costlessly remove it. Doesn't matter. The key point is that start from the network as a whole, keep on peeling off the first, the weakest link, then the second weakest link, then the third weakest link, and so on. And this red line, this one, represents the spectral distance between the thresholded covariance matrix and the target Ledward-Wolff analog. So this represents the the distance between these two spectra. The idea is that you keep on going, and after a while, this is empirically observed. We don't have a mathematical proof for it, but after a while, the distance goes up. Wherever you have the minimum distance, so then essentially the thresholded matrices spectra is the closest to the Ledward-Wolff spectrum. That is something that we are calling maximal filtering. So this is the maximum amount of filtering that you should do. If you go any further, then the spectral distance again starts increasing. So you just stop. That is the maximum amount. As you are getting the closest to that. Now, if you add up the cost of edge deletion, then if you just take the sum of these two, then that gives you this black dotted line. So here, for example, if you believe that edge deletion is costly, then if you add that, then you get the minimum here, which we call tuned filtering. The intuition is very simple. If there is a cost of edge deletion, then you have to stop before maximal filtering. Maximal filtering is if there was no cost whatsoever, then how far could you go? Now, if there is cost, then you stop before maximal filtering. So we get this is roughly speaking a visual of maximal and what we will describe as tuned filtering. Now I will just give you one simulation example. I guess I have only a few more minutes left. So let's say this is the true network. So what does it mean? This is something that we are imposing by hand. That let's say 4 and 5 are not connected. We are putting in the covariance matrix, we are putting the covariance between the 4th node and the 5th node as literally 0. And the edge weight represents how strongly they covary. So 5 and 6, for example, very strongly covary, and so on. So 2 to 1, strongly covary. Similarly, 7, 9, 10, they create a triad. So again, this is just imposed by hand. Now, obviously, if you then simulate it, then due to sampling fluctuations, everything will be connected to everything, because in small sample we will recover some amount of correlations. So here I know the true data generating process, and this is the simulated analog of it. Now, this is not unique, obviously, because if I run another simulation, then there will be something else, but which will be very close to it. So once we apply the maximal filtering, then this is what we recover. This is the maximal filtering. And once we apply some parametric tuned filtering, then this is what we recover. The takeaway is that, for example, the maximal filtering recovers, this 2, 1, 6, 5, and also this triad 7, 9, 10. Now, if you go back to the original, network, then this 7, 9, 10 is there, and 2, 9, 6, 5, 2, 1, 6, 5 is here. So just the takeaway, I guess, is simply that it does a reasonable job, at least in terms of recovering only the strongest connections. So this is a simulated example. Now let's see some real data. I would just get into that. So here we took NASDAQ data. In our paper, we did a whole bunch of other exercises. This is just one example to convey the basic idea. We took NASDAQ data for 50 stocks for 70 consecutive days. And anyway, this is the usual return thing that I have just described. So if this is the sample covariance matrix. So it's basically a giant block where nothing is visible, and it's not clear which one is more important to the other, and so on. So what we are plotting here, if you look at panel C, is that there are 50 nodes. So there will be 50 C2 possible number of connections, right? So we are rank ordering them from here to here on this x-axis, right? So 1, 2, 3, 4. Rank ordering in the sense that the smallest weight, then the second smallest weight, then the third smallest weight, and so on. So what this line represents is that you keep on removing one of these edges. You remove one edge, find out what is the new eigenspectrum, find out what is the distance from the Ledward-Wolff analog of the original matrix, and then plot it here, whatever is the distance between these two spectra. So as we can see that the minimum is here. So maximum number would be 50 C2, which would be probably something like 1250 or whatever, something like that. So maximal filtering removes a massive number of edges. So where you are left with basically this one. where some of the nodes, some of the stocks basically do not have any more connections left. But obviously you could have stopped here as well, or here, based on here we did not assign a cost curve like this. If we did, then we could have stopped here, and then a few more connections maybe would have popped up, right? So this is an example on the on the data. So let me now just quickly summarize, because I guess I'm close to the finishing time. So here what we have proposed is an algorithm for maximal and tuned filtering. The idea is that we can apply it to complex networks, and more importantly, this applies to the high dimensional data. Now, if you really do not have high dimensional data, so suppose you have, let's say, the number of observations is significantly larger than the number of entities, in that case you would not face this problem, and in that case the Ledward-Fulp analog would be very close to the true, to the realized covariance matrix to begin with. So then this algorithm would not be very useful unless you have a high dimensionality problem. So this is sort of geared specifically towards financial market. Having said that, my co-author in this paper, who is a statistician by training, told me that in case of genetic data, again, there is a very similar problem that people face, because the number of possible entities can be very large, whereas for each of them, they can observe only a very few realizations. So the same high dimensionality problem pops up there as well. I didn't add that example here because I do not know much about genetic data, so we skipped it. But the point is that the application of this algorithm goes much beyond that, much beyond only financial network. And here we have sort of used some local geometric property and its spectral structure. And I guess the important feature of this filter is that it has very nice statistical properties along with retaining very good spectral properties. And this is something that I would like to differentiate from some of the other known filters. So if you look at the literature, at least in the case of financial markets, there are some algorithms like what are called the planar maximally filtered graph or minimal spanning tree, and so on. The thing is that none of them have good statistical properties. Those are kind of optimization based approach. They take whatever network that is given as representing the true data generating process. There is no question of a false positive or a false negative in terms of realization of edges. There is no statistical concern. There is another filtering approach. What it does is that it takes individual edges to represent. It takes a statistical approach to validate whether some edge should exist or not, but they do not have good spectral properties. They're purely statistical. So here we think that probably this kind of nicely combines its statistical properties along with spectral properties. So currently this paper is we are circulating this paper and it's under review. So all sorts of comment would be very useful. Sherry, especially, you have been doing this kind of work for quite some time. So, and also from the rest of you. So I guess I will stop here. Thank you very much for listening to me. Yes, Sherry.
So Anindya, that was very, very interesting. I have some experiences, in filtering correlation matrices, right, using random matrix theory and so on. So my problem is with the correlation, price-based volatility matrices or price-based correlation matrices. They suffer from this paradoxical risk measure problem, i.e. that during a boom, volatility is low, correlation is low. During a bust, correlation jumps up, right? So when we sort of then did a regime switching estimation of, in other words, trying to overcome this problem of boom, this paradoxical way in which these risk measures behave. This may be of relevance even to Rosella's measurement of stochastic volatility. Stochastic volatility models really don't overcome this problem. During boom, volatility is shown to be very, very low. And then during the bust, it jumps up, but then you don't get any forewarning of this switch from low volatility during a boom, and then a big jump when the markets start falling. So when we try to filter the correlation matrices, we first sorted out this problem, and then did this random matrix sort of methods of Marchenko-Pastor, and and then of course to sort of see whether or not this sort of, so we did a prior correction for this correlation problem, and then when we did the random matrix filtering, we got a much better outcome than if we didn't. So that's a comment that I want to make just from experience of work that we've done.
So one thing that I would like to just add that, I mean, basically we are proposing a solution pretty much to account for that. But here the solution is as follows: that let's say you have data from here to here, then there is a problem, because as you're saying that it's contaminated by high volatility and low volatility. Now, one obvious solution is, why don't we take only from here to here, let's say. Then the problem is that the number of entities can be much larger than the number of time points, and in that case the covariance matrix estimation would not be statistically legitimate, I mean statistically credible and correct to begin with. It will not, the problem that I showed, that the eigenvalues that you will estimate from the sample covariance matrix will be all over the place. They are not correct. So in that case also, one cannot even go to the realm of application of random matrix theory and so on. So here we are proposing basically a theory around that suppose you really chop off and just try to work with only this much. Is there even a credible way to do that? And our algorithm basically tells that, yeah, you can do that. Just apply ladder proof and then try to, these are all shrinkage estimators, so then try to shrink the eigenvalues correspondingly and then use it as a filter. It will just work just fine. You will recover most of the the true covariance values which are there. The ones, and that is also what we show by simulation as well, that it has good small sample properties. So yeah,
right. So you make an interesting point that we shouldn't over filter, right? You're saying there is a maximal amount by which of filtering that you should do. That's very interesting, because normally we don't know how much to filter, right?
So what we are saying is that if you simply go by the spectral structure, then you can filter a lot, but then that might be just too much, because filtering is also costly. I mean, you're throwing away information. So then one should actually account for that. And so what we are doing is that from zero filtering, which gives you the original network to begin with, it gives you a upper bound in terms of maximal filtering. And it gives you a way to sort of interpolate between these two, limits.
Okay, thank you.
Thanks. Yes, Kurt. You're on mute, Kurt.
I'm unmuted now. Thank you. That was fascinating. This is fascinating, particularly because we face a very, very similar problem in the neurosciences, trying to estimate the underlying directed connectivity in neural networks from usually quite sparse data, say from EEG electrodes and the like. So one thing which preoccupies our world is the distinction between a filtered network that's composed of directed versus undirected edges. So is this particular kind of filtering, the sparse filtering, does it give you an underlying adjacency matrix, or what we would call an effective connectivity, which is usually much sparser than the correlations that we would call a functional connectivity? Is it directed or undirected?
This will be, so given that I'm working with covariance matrix, after I filter, it will still remain basically a subset of all the original edges. So therefore, it will still be undirected. But this one, I can convert it into a filtered sort of adjacency matrix. So if I start from a known adjacency matrix, I filtered it this way. Whatever is what I get, I can represent it basically as a thresholded adjacency matrix, basically. But it will not be directed. It will still be undirected, because the starting point is an undirected covariance matrix.
So
yeah.
If you wanted to start, I'm just mindful of, I know Tim's gone now, but remember Tim's sort of no backward causality, or no jump back, which seems to be a very important sort of aspect of asymmetry, and that would necessarily, certainly in the sort of time series analysis, require an asymmetry in the adjacency matrix. And of course, that's going to induce complex eigenvalues. So I'm just wondering how you'd handle complex spectral characterizations. And
there will be that's actually a very good point. In this framework, it will not be feasible, because here then the target, the Ledward-Wolff analog, which gives you all the consistency properties and so on, that is only for covariance matrices. So if you take, for example, partial correlation or something, which then introduces direction, then we don't have a Ledward-Wolff analog, as far as I know. Now, because we are treating Ledward-Wolff as the target, spectrum, then I have to find out a different target spectrum to begin with, which is actually a very important point. I never thought about it, but yeah, I do not know the solution as of now. This is all in undirected graph.